Well, I think we're about start time, so I'll go ahead and get you guys started. I'll start with a couple announcements. The first one is related to our 199 class. As you know, at least I think you know, it's a big help. And many of you I know have been taking advantage of it. And unfortunately, for the first time, we've had to, or Don's had to say to a few of you, I can't give you an ad code. We just have too many. And anyways, through some effort, that has changed. So if you're one of those people who Don had said you didn't have an ad code, that has changed. So please get an ad code. We'll have to do a late ad. It's a little more complicated. I told Don about it, but it's well worth it. And so I want you in there. I want you to take advantage of it, and actually it will help in the next process of this next step. As you can see, we've got a lot of students in here, and so I'm hoping that I can use our large numbers in this class and then the large numbers in the 199. So that's what I want to make sure, and so and use that as justification going forward next semester to either have more sections or more rooms, or some kind of way of getting out of having so many. So bottom line is, if you didn't get into that class, it would be helpful, A, to you, and then B, to us as a department, and then C, to everybody else as we go forward next semester and as I fill out our needs and whatnot. So anyways, I want you to have the class, and I think Don even told a few of you, well, I can't really add you because that's over the limit, and we'll just kind of have you kind of come and do it anyways. But now the approach has changed a little bit. I want to cram it in there and make it look and use that as a justification. So please get an ad code, do the paperwork for the late ad, and get in there. So that's announcement one. Announcement number two, I know the syllabus has a starting pay, chapter 25, but again, as I was looking at it, I realized that this could be a pretty long chapter. There's some tough ones to do. I think I did some pretty good examples for you on Thursday with symmetry arguments. There's some other neat problems to see also, so I thought maybe I ought to address those. I really didn't say anything about the field inside a conductor, so I thought I better start this week with really continuing on. So that puts us a little behind, but I think in a good way, in the sense that I think it's needed. At least that's what I was thinking until I walked in. Looks like a lot of people turned in 24, although maybe not even close to the whole class. So maybe I should stick to what I was thinking and say, okay, let's do some more from chapter 24. Let's see if we can get that to sink in a little bit more and do some examples. And partly because last Tuesday, if you recall, I continued with 23, and that really is what got us behind. And so if I don't continue that, I'll cut chapter 24, I think, a little too short. So anyways, with all that said, I'm looking at people's faces, and should I do a little bit more from chapter 24 before we go into chapter 25? Okay, good. So I do see some people's look that yes, I should, despite the few other feedback I had earlier that they were ready to move on here. All right, so that's what I want to do here. So maybe as much as the hour and a half like we did last Tuesday, which got us started, like I said, a little bit late. Let's do that same thing. And the good thing about this particular semester is we do have a little buffer space here. We don't do nearly as many chapters as we did in 121, or as many as we do in 123 here. So we don't have to do. In fact, the first 5 weeks, we have 5 weeks to do 4 chapters. So that gives us that extra little buffer space. We don't have to do a chapter a week to stay on schedule here. However, some of these chapters are pretty tough, and maybe you saw that already here. So let me say a little bit about the electric field in the conductor. In fact, your author does this. He gives you 4 bullet items that says, hey, let's think about the electric fields and conductors for a moment here. And so let me put the first one here on the board. I started to write it before class. Let me finish here. But he says this, that the electric field is 0 everywhere inside the conductor, or inside a conductor. So that's just a good factual piece of information to carry with you. But it's worth stopping and saying why. Why does the electric field have to be 0 everywhere inside a conductor? So let's say this is my conductor. Has no symmetry in its shape. I'm not worried about that. But what if there was, say, an electric field somewhere inside, like that? What would happen? What's the whole definition of conductor? Yeah, the electrons are free to move. In other words, they'll move if they get pushed, right? So what would an electric field, if there was an electric field, what would that do to the electrons inside? That would push them, right? Right? And so we learned that the force on an object is the charge times the electric field. All right, so if the electric field is pointing this way, and there is an electron right here, so it's a conductor, it would have a force on it. And would it move? Yes. So unlike an insulator would say, okay, if there's an electric field inside an insulator, yes, that puts a force on the electron. But so what? Can the electron move? No. But the difference is right here. A conductor, the electron could move. In fact, I should even ask, what way would it move right here? Left or right? You guys didn't say that real quickly. Which way does the electron move? Isn't it this way? Isn't it left? Isn't it a negative charge times the electric field, right? Isn't the force in the opposite direction of the field? Wasn't that the whole point of talking about field and not force? Because the field has a well-defined direction. But what force is, it depends what charge I put there. And our definition of an electric field was the direction that a positive, a small test positive charge would move. Do you remember that from our definition of electric field? And so if there was a positive in here that could move, the positive would move in the direction of the field. What direction would the electron move? Opposite of that. And you can hopefully see that in the math, that there is a direction to the force. And because you're multiplying by a negative charge, the direction of the force is negative of what the field is. And so the electron would go that way. Well, probably good I stopped and mentioned that, but that wasn't my point. My point was there is a force on the electron. It would move. When would it stop moving? Well, okay, you might say it moves all the way to the edge. Fair enough. But if there's still an electric field in there, then it would push a second one and a third one and a fourth one, right? And every time it starts pushing an electron, maybe to this side, which means they're now missing from in here, or maybe the next one moves over, and so maybe they're missing from all the way over to here, doesn't that then create a field from that positive to that negative? And then what happens between those two fields when you add them together? They end up canceling off. And so my point is this, that this is why we would say the statement that the electric field inside a conductor is going to be zero. Maybe not right away, because it will take a while for these electrons to move around. But the point is, if there is a field, it will then push. And they will rearrange themselves. And as they rearrange themselves, the electrons that come from the conductor, together with the electric field that maybe was created by some other charges that were out here. See, maybe this came from the fact that I had a plate that was positively charged and another plate that is negatively charged. And so there was a field there, and all of a sudden I put a metal piece in between it. And you might say, oh, that would make an electric field through the metal piece. Well, for maybe a small moment. Because then that electric field would push the electrons, and the electrons would move around, and those movement of the electrons would create a secondary electric field, and the two electric fields together would cancel each other. How would I know they would cancel each other? Because what if they didn't cancel each other? Well, if they didn't, then there would still be an electric field. And how would happen to the electrons? They would keep moving, and so when would they stop moving? When there's no more force on them, which means there's no more field, right, exactly. And so there's our argument that we know that the electric field inside a conductor is 0. And so we'll do a homework problem. I know you had a homework problem on it. It asked you to draw the field and get a good physical intuition for the field inside a conductor or the field with a conductor near it. In fact, that's one of the experiments you will do this week in lab. Today's lab is about electric potential and electric field. And I hope we get that far today to have electric potential. Because we're going to use electric potential to find electric field. And one of the things we're going to see in tomorrow's lab is we're going to put a conductor in there. And we'll see that the electric field in the conductor is 0. It goes away. You'll make a little measurement. Well, let's look at number 2 here. Any charge that is on an isolated conductor resides where? And hopefully by now you've got a chance to read this and study it and to memorize that. Hey, the charges on a conductor should be on its surface. And so you take any conductor, and I brought this one out here for just kind of show and tell. It's kind of got a weird shape to it purposely. So we've got, something we can talk about that's not completely symmetric here. But if I were to put a bunch of charges on here, okay, so let me erase this picture, but this one is a continuation of the one we just did. What if I then, hey, okay, here is my conductor. And let's say I can reach inside and put the charge right there. I'll put it right inside. It won't stay there. Well, why not? Yeah, it's really back to exactly what we just said. You put it there, then there would be an electric field, right? And that electric field would then push, and things would push on each other and move around. And so this thing, as we kind of drew before, would eventually end up pushing itself all the way to the edge. It's at the edge where it comes to the edge of the conductor where then it's kind of forced to hang on. Because of the other positives that are in there, it can't go into the air. But you put it anywhere in the conductor here. And that, if you did a little Gauss's law around it, that would give you some kind of an electric field. And that electric field then can't exist, as we said in the step before. We can't have it. It will shift around. So the only thing you can do is eventually say, and your author does it this way, he has this shape, and he says, look, using that argument, if you drew a Gaussian surface right at the edge of your conductor, okay, you've got to get 0 flux through there. Why? Well, because we just said the electric field everywhere inside is 0. So if we are just microscopically inside our conductor, then this integral E dot dA gives you 0, right? Because there's no electric field. So you take no electric field across the surface, you're going to get a bunch of zeros plus 0 plus 0, and the total is going to be 0. And the other side of this equation is the charge that is inside. And so the charge that is inside is 0. And so he uses Gauss's law to make this argument then that what will happen to charges is they will shuffle around inside a conductor. And that's the second important point I want you to realize. They will shuffle around and be on the outside. So put them anywhere you want, they will get to the outside. I brought this out as a prop to kind of show you again. Here's the Vandy graph. Do you remember me doing this one? Maybe I'll turn it on again, but do you remember how I got it charged up? Remember I said there was rubbing going on here? Now, if you look closely at this, it used the advantage of conductors purposely. It rubbed here. The electrons came off and went on these wires. And from those wires, it could flow through the conductor. And this metal top, if you will, is placed on top so that that metal peak there is touching there. And so the electrons will do what? Even though you've rubbed them off, even though you've placed them inside the conductor, where do they end up? Yeah, on the surface, on the outside. So when I turn this crazy thing on, right, even though all the rubbing is going on the inside and it's touching the inside, eventually those electrons, as we saw before, work their way to the surface. And that's our Gauss's law. That's why that rubbing on the inside works well, because we're taking advantage of this conductor. And if that top piece wasn't a conductor, then the rubbing and the electrons would have stayed where they are on the inside of that. And so again, as we set up a problem and as we think of some of the engineering techniques that we're going to see, we will see an advantage. I shouldn't say advantage, I should say different properties between conductors and insulators. And sometimes you want that property, so you use a conductor. Sometimes you don't want that property, so you don't use a conductor. Or you want the properties of the insulator. And so they play a different role there. And so that's an important point, if you will, number 2. Number 3, your author goes on to say, keep this in mind about conductors. He says that this electric field just outside a charged conductor is perpendicular to the surface. And, well, I'll pause right there. Perpendicular to the surface. So what are you trying to say here? Well, again, maybe a picture over on this board would be helpful. But if I were to start out with something that looks, say, like this, so here is a positive charged plate. Here is then a negatively charged plate. And this is one of the examples I want to do today. This is going to create an electric field. It's a good way to get a uniform electric field. And so it may look something like this. But if I come along and put a conductor in here, let's just say I put a sphere. So there's a aluminum sphere. Will the electric field be inside the conductor? No, that's what this is, right? Okay. And so what will happen, as we mentioned, is that this field will get canceled. It'll get canceled because the field there actually forced one electron to move over to here and away from there. You might say that that canceled field is really made out of 2 fields. It's made out of the one that was generated by these external charges, and then one that was counterbalanced by the field from the distribution of charges from there. But eventually we end up with no field inside our conductor. But I'll do you one better than just no field inside our conductor. The field that is just outside, that is coming towards the metal conductor, is then going to hit the conductor at 90 degrees. It's going to be perpendicular.
Isn't that a three-dimensional star shape with a lot of points? Would it still be perpendicular?
Yes, yes. And we'll do a little pointy one here in just a second and talk about the pointy edge versus the non-pointy edges here. So we're good. We're building up to that one here. But the argument of why they have to be perpendicular is the same argument of why the electric field has to be 0 inside. Because what if it was not perpendicular to the surface? I mean, if I had this over here and say there's that negative charge and there's the electric field coming in right there at some angle, non-perpendicular, you could say that that electric field is really made up of a piece that is perpendicular and one piece that is tangential. Fair enough? Now look at that tangential one for a moment. What would that tangential component of the electric field do to that electron? It'll push it tangential along the surface. And can it move along the surface? Yes, and it will. And when will it stop moving along the surface? Yeah, it'll keep shifting around. All these electrons will shift around until there's no more sideways forces on it, right? Which means there's no more sideways electric field. There is no more tangential electric field. And so this electron's going to move over to here. Whoops, here. In the process, it'll make a, you might call an internal field that will cancel that one. And what you will be left with is just a field that is perpendicular to the surface. And it can't cancel that because it would have to move off the surface to cancel that. So it can't do that. It could move anywhere in the conductor. That's our definition of a conductor. But again, just like we argued that the electric field has to be zero here, because if it wasn't, they would shift around until it was zero. The same thing here. The argument is that if the electric field had a tangential component, the electrons on the surface will shift around until the ones that are shifting around cancel the external one, and the total field now is going to be perpendicular. So a good drawing of this electric field would be something more like this, that once I put the conductor in here, I will not get a field inside. That's because charges shift around. But I also will not get a field that is that is tangential to the surface. I could only get ones perpendicular. And so this little aluminum ball has an effect that, if I was guessing, might make and disturb the electric field something like that. And that's what I get out of this picture as I think about what's going on with the conductor and the movement of the charges. And so there is probably what the electric field roughly looks like when it started out nice and uniform between the two charges, and all of a sudden I throw a conductor in there. I know that I can't have any field inside the conductor, and I know what I do have must be perpendicular to the surface. Okay? And so that's what I wanted you to see here. And I know it's a homework problem, and even an example one I'll do here in a few minutes here, is what's going on here in terms of the electric field. And again, you'll see this very similar pattern when you do the lab tomorrow. Although we've got so many other things going on, we're trying to see that one, that I don't think that, I think this is the least clear of the 5 experiments you do tomorrow there. So, but nonetheless, we'll see how much we can deal with it. In fact, I'm not done with this statement, because not only is it perpendicular, but it has a magnitude that is equal to the charge density over the permittivity of free space. So in other words, these charges here are going to shift around, right? And that charge density may not be uniform. It depends if the electric field on the ball is uniform. But your author and I will draw a little picture here. We'll do a little Gaussian surface. If I then apply Gauss's law to this, like we did on Thursday, let me pick a little Gaussian surface. And I think the one to pick is kind of that cylinder looking shape. And I'll make it really, really small. I know in the picture I want to draw it a little bit bigger so you can see my Gaussian surface that I'm trying to draw here. But you have to think about this in the limit as I get smaller and smaller and smaller, because I just want to get right above the surface. And so as I get smaller and smaller, this part right here is just above the surface, and this part back here is just inside the surface. Okay? And so if I apply Gauss's law here, you might say because I have a cylinder, there is really 3 pieces to that cylinder. Fair enough? There is what you might call surface number 1, which I'll call the inside face, or edge, or top, bottom, however you wanted to call it. I'll call this number 2, the one that's on the outside, and the one that I was calling the face, the one that kind of wraps around, number 3. I'm hoping you can see number 1 is 0. Why? Okay, it's inside. What about being inside? There's no electric field inside. Exactly. And so we're going to use that idea that, hey, there's no electric field inside, therefore there's not any flux on that surface. Okay? How about number 3? I'm hoping you can see that one too. So remember I said these Gauss laws are very visual. Got to look at the picture. Yeah, I heard a couple of you say it's going to be 0 too. Why? Right. I guess there's kind of 2 parts to this. The part that's still inside the conductor, well, the field's going to be 0, just like that one, okay. But the part that is outside of the conductor here, okay, and again, if you're making this thin enough and small enough, we just argued that right at the surface, that the electric field is perpendicular to the surface. So the electric field is pointing straight out, meaning the electric field is going straight out through surface number 2. But the surface that wraps around, it doesn't go out. It's at 90 degrees. And so there's my argument there about the flux there would be 0. The only one that's not 0 then is number 2. And fortunately that's an easy calculation because I'm going to say I'm right near the surface. I can take my surface small enough, if you will, to say, look, whatever's going on in the big picture, I'm not saying that the electric field doesn't change over the whole surface of the ball, but in some very, very small, minute space, I could say that the electric field is uniform in the limit that gets smaller and smaller. So I'm going to say the electric field right here at this surface number 2, or penetrating surface number 2, that's the electric field I want to know, microscopically close to that surface. And so that's what I will call the electric field E. But what I can say then is I can pull it out, because it is the same. And more than that, as we already said, we can say that it's perpendicular to the surface. So the angle here is 0 degrees. The electric field is, straight out from the surface, and then our surface is right up against the surface of the metal conductor here. So that's cosine of 0 degrees. And so this just becomes EA after all that. And so then finally, bringing the A to the other side of the equation, the electric field is the charge that is inside divided by A over epsilon naught. And the charge divided by A, isn't that what we mean by the charge density, the charge on the surface? How much charge do we have enclosed would be that minute amount of charge right there on the edge of the conductor divided by the area of that. That's the charge density right there on the surface over sigma. And so that was my point that I said this is the electric field right near the surface. Please don't confuse that with what we left off when we left on Thursday. We had this equation, didn't we? They look a lot the same, don't they? What was this one good for? Yeah, this was a sheet of charge. And because we had this sheet of charge, we had an electric field on both surface 1 and surface 2. So the difference between the calculation I did on Thursday, where I came up with this, and the one I'm doing now for you really is back here. We did not get a 0 on Thursday for that one. We had a term here, which was the same as that, and that's why we got the number 2, and that's why we got a 2 downstairs. So there was an electric field on this side. But you can see here that the charges have rearranged themselves in a different pattern. So on the conductor, so you get a different equation to the electric field on that conductor there, and right on the surface of the conductor here. Okay. All right. Well, finally, then, and I think this is the hardest one of all. The mathematics is really kind of beyond the scope of this level, but conceptually I think we can still nail it down here. What about a charge that is placed up on a irregularly shaped object? It is a conductor, so all these other things would be true. I place a bunch of charge on a funny shaped conductor. That's why I grabbed this one for a visual effect and say, okay, what if I put all this charge on this irregularly shaped conductor? Well, that first one up there tells me that if I tried to put the charge inside the conductor, it would migrate out. And so if I have something that looks like that, and I put some charges in here, well, I can't get a field inside it. They're going to flow around. They're going to flow out and go onto the surface. And they're going to rearrange themselves on the surface in such a way that the field coming from it is going to be perpendicular to the surface everywhere. It's going to have a value here of sigma over epsilon. But will it be the same sigma? In other words, will the charge be evenly distributed on this object? And the answer is no, and hopefully we'll see it here. The charge then will accumulate different amounts depending on the curvature of the of the metal there, where you are on it. The curvature. Let's see if I can say that. Accumulate at the locations where the radius of curvature of the surface is the smallest. I like to say at the sharp points, that's where your charge is going to accumulate here. Drawing a picture here, here's what it would look like. Drawing this one, and then maybe better still going to this one. But if I put a bunch of charges on here, they would not stay in the center, if that's where I place them. They would migrate to the surface. How would they accumulate? Well, you would get some spread out. And this looks like the same radius of curvature. So along here, they would have the same concentration, but that concentration would be different than areas that had a different radius of curvature. And the whole point of putting this pointy end on one side and a more rounded one on the other side was to get you to think about this whole idea of where would the charges go. And without proof yet, I would say that they go to the sharp point. And so here would be a lot of charge. The charge would really accumulate here at this sharp edge. Over here where it's not so sharp, I would get some, yes, but it would be less concentration. And hence that less concentration means I have less of a sigma. That less of a sigma means I have less of an electric field. And so if I was drawing the electric field that came from this, and they're negative, I guess I would be drawing them this way and be very concentrated here, hitting the surface perpendicular. But here not nearly as concentrated. Not nearly as strong as a field. And so this ends up with a high field. This ends what I will call a medium field. Because what about these areas here? They're kind of flat. Well, they would have an even lesser radius of curvature than that one. Now let's see if we can get a conceptual picture. Like I said, the math really involves some of your math. When you do your multivariable calculus, 200 here, which again is beyond the scope of the book here. Probably not beyond the scope of your education. But your author just takes a little different approach, and I'm going to too. I'm not going to try and prove it mathematically, but I am going to try and prove it conceptually here. Let's think about what is going on. Remember these electrons. Why would they spread out across a surface anyways? Yeah, they're all negative. They don't like each other, right? As soon as they get too close, they push. If this shape here was a perfect sphere, I could probably argue that the charges would be evenly distributed. Why? Well, because if I had a bunch that were clumped together, wouldn't they push much harder than these guys? And as they push, wouldn't that migrate over? And so they're kind of balancing themselves. And they push as far away from this one as possible, but without getting too close to that one. And so they kind of balance it, right? But don't forget this, that the conductor itself has no field in it. So if I put a little electron right here, the electric field that is generated from it looks something like, and let me just say this one electron. So I'm going to go ahead and draw one perpendicular to the surface. But the electric field from that one electron might look something like that, right? And so if there was another electron close to it, it would feel the effect of that electric field and say, oh, get me away from here, push me away. But if you get too far away from it, what I will call over the horizon, the electric field does not touch you anymore. Does that kind of make sense? It's kind of like saying, if we go out to the harbor here and you look at a boat sailing off into the distance, what's going to happen at some point is you can't see the boat anymore. And not because of the haze, which often happens, but what's going to happen as that boat starts to sail away? It goes over the horizon, if you will, right? It goes what you might call, over the arch, and you can't see it anymore. Your visual sight is now gone. The earth looks something like this. You're standing here looking at it, and your eyesight looks, and if the boat is here, great, you can see it. But when the boat gets over here, you can't see the boat anymore, right? And so what I'm trying to say is the same basic idea of this electric field. It's going to be pushing out to the sides, but if the curvature is really small, the radius of curvature is really small, then you don't have to go very far before that next electron is kind of over the horizon, if you will, and you can't push on it anymore. And that's why these electrons don't mind getting real tight together. They are far enough away that they can't see each other. They don't push on each other. The metal conductor has blocked the field from going through and pushing on each other. Just like you can't see the boat because the earth blocks the light from going through the earth. You can't see the boat anymore, right? And so same thing here. And so that's why then something with a small radius of curvature can build up a lot of charge on it and yet not here. Okay? Now, don't get me wrong, it does have some other effects, which I hope to show you in just a second, because that also means that right here I can get a very strong electric field. And so if I want to make strong electric fields, I put them with little points. And that could be a good thing or a bad thing. If you want to use the electric field to push charges and accelerate them really fast, you do want a big electric field. On the other hand, if that electric field gets so strong, it can have an effect on the air. It can ionize the air, and the air can get ionized, and then that can neutralize your charge here. So these pointy edges can kind of be a bad thing if you wanted to build up a lot of charge. Did you notice what shape I have on the Van de Graaff? Any sharp edges? No, it's designed to have a pretty even, smooth surface. Now, the radius is not quite the same this way as this way, okay? But it does have very gentle edges, and charges don't build up so much that they leak off. And so this has a tendency of building up quite a bit of charge. And so you saw that. You saw this little spark here that, gets generated. And it'll build up and eventually come off the top. Now, if I were to change this, and maybe I turned off the lights too much, but I got the heat lamp here. Can you see this pointy edge? What do you think might happen if I put the pointy edge on there? And maybe now so you can see it. What's going to happen to the charge on that pointy edge? Isn't that where they're all going to go? In fact, they'll go there so quickly that there'll be so many electrons there right away that they will then ionize the air right above it and leak off. And so this ball will never get a chance to build up charge. You see any sparks? No. That little pointy edge is fouling it up. If I wanted to make sparks, it has got the charge off of it. If I take the little pointy edge off, now the charge is spread out across that ball, building up a lot more of them, and then hence enough that they will rip off and tear off the side. You can see it again when I do one more step. Let me take that little pointy edge and cover it, and in place of it I'll put some wires that got pointy edges. So if I put this on, any guesses when I help let the charge build up? Where's the charges going to go? To the little pointy edges, right? They'll get so many there that they'll leak off, right? And when they leak off, isn't that kind of like a little jet? Isn't that Newton's third law of motion? And so those electrons are coming off the edge, and that's what's making that thing spin around. If I stop the charges from building up, you'll see that the thing slows down. And they don't have the little electrons racing off the end of it here. And so this is my little jet. Instead of taking molecules and burning them and sending them out the back, I'm taking electrons that are charging them up and sending them out the back. And I have more of what you might call an ion engine than a rocket engine. What are you going to say? Yeah. And so there's my little demonstration here of the pointy edges, and the pointy edges do leak it off here. And like I said, there could be advantages and disadvantages. It depends what you're trying to do. If you're trying to get those charges to leak off, this is an excellent example of, and we don't really see them in our part of the country here, but you put that little sharp pointy edge on top of a house, and you hopefully save the house from getting struck by lightning, right? And so this will keep the charges from building up on the house as the thundercloud builds up, and the lightning hopefully will not strike there. And then, of course, usually as a secondary effect on the houses, then they do put a cable up there and then down to the ground. So if it does strike the pointy edge, then it goes down, it goes through the cable and into the ground, thereby also missing the house. And I think most people understand that cable being connected on down, but I don't think they connect the little pointy edge with being a anti-lightning strike device there. And so that pointy edge will build up the charge. Oh. Can I tell your story? Weren't you on the lake?
No, it was a lake.
Oh, you were on the lake, Lake Tahoe. So it's on a flat lake, right? Where's the tallest thing around if he's out there fishing on the lake? Right? He's the pointy edge is on his fishing pole, right? Thundercloud comes overhead, right? And what did you hear? You heard the crackling and the hissing coming off that pole, and it was leaking off, and you were about to be struck by lightning. You were in a bad place at a bad time. I'm glad you're here. All right, but that is what the whole idea of that pointy edge will do to it. And like I said, that could be a good thing and a bad thing. If this is spark plugs in your car, okay. If you've ever looked closely at a spark plug, they'll often do this. And if they're done right, they last a much longer time because the piece of metal comes down and they make a nice flat edge off the bottom. And what they're trying to get is the spark to jump from the one conductor to another conductor and make the spark. But if you have a pointy or a sharp edge, if you file it down wrong or it gets scratched or scraped, you'll have a sharp edge and the charges will build up on that edge every single time. And that's the part that will wear out. And it won't take long for then the thing to be worn out because you've always used the same part of the metal. And instead of the spark plug lasting 100,000 miles, we're now at 60,000 miles going, it's just not firing right. And that's because they've always fired off the same edge. So you don't want them to fire off the same edge. You want them in a nice flat surface to spread it out. And so sometimes the spark comes from here, sometimes the spark comes from here, and sometimes the spark comes from there. And you want to get that spread. I picked this shape because I'll never forget years ago, I was in an assembly plant, and they were in the process, and I forget now what they were assembling, but they had metal pieces that looked kind of like this. They were, I think, part of a shelving unit. They were curved around like this. Real long pieces. And before that, they had long pipes. And it was kind of neat to watch them. Like I said, I was on a tour, and they were kind of showing us how they looked at it. And they were painting it what they call electrostatic painting. And what they did is this long pipe came through, and the operator of the equipment took a, something that looked kind of like this. And as the pipe came down and was being held by some machinery, but he would take this, which was hooked to a long cable, and this would build up a charge. And he'd put it inside the pipe and let it go, and it would spread out. So in other words, it made contact with the pipe on the inside. And this end was plugged to something that looked like that Van de Graaff. And because it charged up, well, guess what happened to the pipe? It charged up because we touched it together, right? Now he's touching it on the inside. But does the charge stay on the inside? No, where does it go? To the surface. So they charged up the outside surface. And I don't know which way they charged it, positive or negative, but whatever way they charged it, then when they got the sprayer out, the paint sprayer came out and it had a little mesh filter that rubbed on the paint as it came out and made a charge on the paint droplets. And so the sprayer was charged, and it was charged opposite of the pipe. So as this pipe came down the assembly line, the sprayer guy would go and just kind of make this dust in the air. And he's only pointing at one half of the pipe. And I expected half the pipe to be painted, and I expected somebody on the other side to paint the other half, right? But guess what happened? The whole thing was painted. Why? Right. The charge was on the whole outside of this metal pipe. And as the dust was in the air, the fresh paint, it would stick on the side he painted, but it would float around and stick on the other side. And in one shot, without going two people backside, this would go down the assembly line, and both sides of that pipe, or the whole rounded pipe, if you can call it two sides, is got paint on it, and they use that electrostatic paint. And then the next part in the assembly line was really what was the clincher to me, because I watched what he did on this one. There was a piece that was kind of a corner piece like this. And so as he came and he clamped on, and he had a different one, then he clamped it on, he built up a charge on it. And he did the same thing with the sprayer. And guess where the paint landed? Well, was there charge here? Yeah, this little sharp edge had a lot of paint. I mean, a lot of charge. How about this edge? Not as much, but still some. And so there was quite a bit of paint on the edges. There was even paint on this. But what happened here? Yeah, there's almost no charge on that inside curve. You try to put a charge here and a charge here, they see each other, right? Again, just the opposite of this, the sailboat going away from our harbor, we don't see it after a while. If the earth had been shaped like this, you would keep seeing that sailboat for a long way, right? And that's exactly what happened. And so really no charge built up on that inside curve. And so as he's painted that piece, it was kind of interesting to watch that the paint landed from about here down to there. And then they did have to have a second guy who then had to discharge it, get rid of the charge, and just paint it with a regular paint without the electrostatic paint and get the charge on the inside because it wasn't building up on there. It was a different shape and a different charge distribution. Okay? And so that's what I'm probably saying too much of, and I should get into the problems there. But hopefully you see the whole idea and the application of that. Well, let's see if I can actually do some examples in the book. And a little different than what you've seen so far. You've seen me do a lot of Gauss's law ones. Not to say that the ones I'm about to do aren't Gauss's law, but they are a slightly different approach, but still very visual. And so again, you will probably discover these problems that you are about to do are either going to be easy or hard. Okay? If you see the visual picture, they will be easy. If you don't see the visual picture, they will be hard here. All right? I'll start with number 8. Number 8 doesn't have a picture, so I won't bother too much with the overhead. But since the next one has a nice picture, I will turn on the overhead. Oh! I'm sorry. Yeah, thank you. I was thinking of our old system, needed a remote. Okay, so I will let that warm up here and do number 8. And then we'll jump into some of the ones that need a picture here. But number 8 says the following here. See if this makes sense. Oh, it's starting to get warm in here too. Shall I turn on the air conditioner? Keep forgetting to do that. We'll turn it way up. It'll make it real cold in Don's area. We'll have to put on a sweatshirt in there. All right. It's a small little room, but a lot of the air goes out there. Look at number 8 here. Number 8 says a particle with charge Q is located a distance d from an infinitely long plane. Determine the electrical flux through the plane due to this charge. All right? So the description is something like this. Here's this charge Q. All right? It is some distance d, and then there is a sheet, if you will, a plane. And for the sake of discussion, they're going to say it's infinite. I'll put some edges on it here, so maybe it's, looks a little three-dimensional here, but it's infinitely long here. I guess if we want an example, it might be this is the charge here, and the plane is this desktop extended out forever, right? And so here's the question. How much flux goes through that plane? You done? Oh, you're not done. If it takes more than 3 seconds, you missed it. All right. How much flux goes through the plane? So there's a question, flux. Answer? No, not zero. Wouldn't the electrical flux look like that? Wouldn't it go through the plane? Right? So here's a long plane. But let's try this. It's part of Gauss's law. If this is the charge, if you wrapped a closed surface around this, okay? So I'm going to do a closed surface. So I'm going to do a surface that's different than the plane. I'll just put a little dotted line around there. Let's wrap a surface. It could be a spherical surface or it could be any shape you want. But what does Gauss's law tell us? How much flux goes through that closed surface? So how much goes through a closed surface wrapped around that charge? Right there, right? I don't need to know anything about the electric field or the shape of the surface I wrapped around. Just if I wrap a charge around a surface, whether it be a cube I wrap around it, whether it be a sphere I wrap around it, whether it be a cylinder I wrap around it, I know that the amount of flux that goes through that surface is that. Fair enough? So you might say that's all the flux coming from this point charge. However, that's not the question. The question is how much flux goes through a plane down here. So now again, look at this picture. How much of all the flux goes through this plane? Do you see half of it? Right? Half of it goes up here, which never goes through that plane. The other half goes kind of down at an angle. And so anything that is headed slightly down is eventually, if this is an infinitely long plane, is going through. So the answer is 1/2 of Q over epsilon naught. That's why I said more than 3 seconds. You missed the point. The total flux coming from that point charge is Q over epsilon. How much goes through the plane is half of that. And so that's why I said a little different problems than that I've done so far in class. But still visual. And still using Gauss's law by saying, how much flux do I have? Well, if that made sense to you. Well, it goes on, and maybe I should go on too. But it says, all right, let's be more realistic. The author goes on and says, well, there is no such thing as an infinite plane. But it is possible that we are talking about d being very short, like microns in distance, and the charge being placed on a substrate of a processor, and this being a centimeter long. So how much flux would go through something like that, where we're talking about we're very, very close to a finite size surface? Answer? Yeah, almost half. Essentially the same thing. A good first approximation would be half, right? And it would be a hair less than that, but that would be a good place to start. And that's what your author is trying to point out. That's just what happens sometime in science and engineering. We may not be able to do a complete ideal calculation, at least within an hour or two, but at least we can build the first generation that way. And that's going to foul things up, and it won't run as perfectly as we hoped. But then when we build the second generation, we bothered to take a better calculation on what the flux is. And then we can make our second generation and our third generation and our fourth generation and modify things, and each one get a little bit better as we go along. And that's, again, what hopefully I've got across a few times, as well as what your author's trying to get. He does another great one here. It's problem number 13. He gives you this picture. I'll just put number 13. I'll give you a hint. More than 3 seconds, you missed the point. Here it is. A charge, capital Q, of 5 microcoulombs is located in the center of a cube of length 0.1 meters. An additional 6 other identical charges of charge -1 microcoulomb are positioned symmetrically around Q as shown in the figure. Determine the electric flux through one face of the cube. Answer? How much flux goes through one face? 1/6 of?
1 microcoulomb.
Okay. And just to do the numbers, he called capital Q 5 microcoulombs. And then the other 6 are 1 each. So I'm going to put a -6 microcoulombs. Oh, let me not forget my epsilon naught. So it should be 1/6 of a -1 times 10 to the -6 coulombs over 8.85 times 10 to the -12. And it must be Newton meters squared, coulombs squared, right? But again, I'm hoping you see where this all came from. The big picture is if you wrapped a surface all the way around it, and so the authors helped out in the picture by wrapping a cube all the way around it, wouldn't the amount of flux coming from there be equal to the net charge inside? the sum of all the charges. And so, yes, we've got a 5 in the center, and we've got 6 ones on the outside. The total charge inside then is a -1 microcoulombs. So that's where the charge inside came. So if you take that and divide it by epsilon, that is the total flux coming from the cube. Now the symmetry comes in here by saying, if you look closely at the way this is laid out, do you see how it would look the same? If you were looking at this picture from any of the 6 faces, wouldn't it look the same? Thereby, wouldn't the flux going through any one face be the same? So if the total flux is this much, then we have 1/6 of that to get the total flux through one face.
Wait, why so you need it 1/6?
1/6 because there's 6 faces to a cube. So this is the total that has to come from the cube, and it's asking for just one face. So, 1/6. Okay. How about 15? 15 has a little bit more math. I think you're getting the point here, but I'll just do one more like this to maybe show you. Here we have a line of charge. It's labeled in brown. It's got lambda here. And it says this: an infinitely long line charge having a uniform charge density per unit length of lambda lies a distance d from the point O, as shown in the figure. Determine the total electrical flux through a surface of a sphere of radius r centered at point O. Consider both cases. Consider the case when the radius r is less than d, as shown in the picture, but also consider what would happen if r is greater than d. Well, let's do the first one, which I think is the easier one. What's the total flux through this surface as shown now? 0. Why? Yeah, what goes in is also what goes out. Or put another way, there is no charge inside of that surface, right? That's what the Gauss's law is right here. The flux that goes through a closed surface. I've got to get a closed surface. This is my closed surface. How much flux goes through there? It depends on how much charge is inside. And as long as my radius, as shown in this picture, is less than d, I would say there's no charge inside. Or put another way, I could do the flux. We learned in the last class what that electric field looks like from a line of charge. Didn't we learn it was kind of radially outward like this? And so it would be going in here and out there. Everything that goes in is equal to what goes out. The harder one it might be, how much flux do you get when your radius is greater than d? And so it changes to look something like this. Okay. Now, will that one be 0? No, why not? Okay, one way to say there's charge inside, another is to look at the picture of the electric field, and that's really why I picked this problem. When you go to do a calculation here, and they ask for the electrical flux, you really have two options. You can either do the left-hand side of the equation or the right-hand side of the equation. In this case, I would say doing this left-hand side of the equation is a lot more work, and I'd stay away from it. I mean, didn't we learn the equation for the electric field from a line of charge? Oh, we did, didn't we? And couldn't we put that in there? Now, the reason this would be a hard calculation is we learned that the electric field from a line of charge goes out like a cylindrical shaped object. And you're asking me to calculate how much flux goes then through a spherical shaped object. And the way the angles meet is pretty complicated. Could I calculate it? Sure, probably in about 10 hours. But look at the other side of the equation. And that's really what I wanted to point out. The other side of the equation will also give you the amount of flux. You just need to know the amount of charge inside. And so I won't do a direct calculation of the electric field. Now, sometimes I will. Sometimes I will have to do it that way because maybe that's the only way. And I'll have to spend the whole 10 hours calculating it, right? Or maybe, you know, that's just the point of the problem, and hopefully the symmetry is real nice and it'll only take 2 or 3 steps. But remember, you got both sides of the equation. And that's what these kind of example problems I'm doing today are about. A little bit different than finding the electric field. Now I'm looking at that electric flux here. And so this is what I would focus on for this problem. I would do this right-hand side and say, look, this flux, although could be calculated from the electric field and the angle, is going to be really hard to do. So I'm not going to actually do the integral. I'm going to do the other side. And then I'm going to do geometry. I'm going to find out how much charge is inside. I'll do this, the permittivity by itself. How much charge would be inside this picture here? Yeah, shall I say that part that's in there is length L for a moment? Because wouldn't the charge inside be lambda L? Of course, I don't want to stop there because L is something I invented, so you kind of know that you should always finish a problem with the same variables that they gave you. So they gave us things like D and R. So let me see if I can get L in terms of D and R. Is that your question? Yeah. Okay, so now going into some geometry, I should probably say that's D and that is R. And so this side of my triangle, which I'll call L over 2, square it, and D squared is R squared. And so now when I solve this for L, I guess this becomes an R squared minus a D squared there. Then I can multiply that by 4, and that's going to be my L squared. So L is 2 times the square root of R squared minus D squared. And so lambda over epsilon times 2 times square root of R squared minus D squared is really how I should finish the problem for the flux. And that way it's in terms of the R, the D, and the lambda is what they gave me. So a little more work there, but certainly I think a reasonable, I don't even say geometry, but it's really just algebra. It's Pythagorean theorem. It's algebra 1, right? What is the length of that side multiplied by the charge density? And I'm sorry, what was your question? L over, okay, so I'm going to call the whole length of it L, and if I make a triangle right here, this is half of it. So from here to here is half of L, so that's where the L over 2. So the sum of the square of the legs equals the square of the hypotenuse, and it's all for L. Well, like I said, I thought those three kind of fit together really nice, and I wanted you to see them. Let's try 50 here. Okay, 50 is a nice one to see. We're going to use it a lot. Fortunately, the results aren't too hard to get, but please remember these results. They are problem 50. How come there's problem 50? There's a little icon. Oh, that's 15. And 13. What's 50? 50 right there. Your author says, let's do this. Let's take 2 sheets, okay? And they're infinitely thin. Oh, let's just call them insulators, okay? Result would come out the same. Argument would be a little different if they were conductors. Let me just call them insulators for now. But the point is they're really, really thin. So we really don't have an inside or outside. That's why it doesn't really matter whether I call these a conductor or an insulator here. Okay? But they're, like I said, they're really, really thin. And then we do this. And as you can see, we're going to do this a lot. Yeah?
How could we have known that they're infinitely thin?
Oh, well, let me read the problem. 2 infinitely thin, non-conducting sheets. So you're told. Because the next one I do won't be infinitely thin. So that's the part I'm telling you. So 2 infinitely thin, non-conducting sheets of charge are parallel to each other as shown in the figure. The sheet on the left has a uniform charge density of sigma, and the one on the right has uniform charge density of negative sigma. Calculate the electric field to the left, to the right, and in between the two sheets. Okay? And that's what I want you to see. What kind of electric field would you get here? Okay? This is very, very useful electrical field. We will do it a lot. We will do it in lab. We will do it when we do our electronics. Some of you are doing it already with your capacitors in your circuits class. I mean, this is the electric field of choice. You'll see why. It's one of the simplest, nicest ones to use. And it's really easy to get this, because what are you really saying here? You are saying that the charge density here matches the charge density here. They're opposite in sign. How do you think you would actually make that? Well, if I took a bunch of electrons off of here and put those there, wouldn't this one then have a positive charge and equal in magnitude to that one, which has a negative charge? So that's often what we will do. And you'll see why here. But we've got two sheets, okay, like I said. Same magnitude in charge, opposite in sign, okay? And again, let's just call them infinitely thin, but also let's call them infinite in length here. Why is that useful? Well, let me give you guys a little bit of room to kind of see over here, and I'll come back over here to this part of the board here, and I'll kind of draw that picture, not as nice as your author has with all the different colors and more of a three-dimensional view. But I need to add to it, and I can't write on the screen. So I'm going to take a cross-sectional view and say, okay, this is sigma. This is negative sigma. If it helps, they go back infinitely far into the board, something like that. Okay? For illustration purposes, I'm going to put a bunch of negatives and a bunch of positives. Little side note here. I guess I really don't know which one's positive and negative. I just know one's opposite of the other. So don't ever fall into the trap that you see sigma and they mean that's a positive number. It's a variable. This could be the negative and this would be the positive. But one's got to be positive, one's got to be negative. And so let's call that one positive and that one negative here. All right? But here's the question. The question is, what is the electric field between them and on either side of them? Okay. Well, again, hopefully this will show what we've been doing. Let me do this. Let's forget the second sheet for a moment. Let's just pretend there was one sheet. We did this Thursday. It's worth doing it again. I even alluded to it about 20 minutes ago when I was doing the electric field from a metal surface. But if I were just to put one sheet up here and give it a charge, and I'll illustrate it with positive, but it doesn't matter if it's positive or negative. The point is it just has some charge density sigma. What electric field would I get from that? Well, remember the Gaussian surface we drew? We drew kind of a cylindrical shape, look like that. And if we called this side surface number 1, and we called this side surface number 2, and we called the wraparound, the face, number 3, and we write out Gauss's law, we would say the integral over a closed surface is equal to the charge inside over epsilon naught. So let's do it again. It's slightly different than the conductor we did about 20-30 minutes ago here, but it would go something like this. It would say, well, you got to do an integral over face number 1, or surface number 1. You got to do an integral over surface number 2. You got to do an integral of surface number 3, because you got to do a closed surface, right? Gauss's law says the flux through a closed surface. So we got to do all 3 surfaces. And if we start laying that out, the argument goes something like this, that if you look closely at this, if this sheet really is infinite, it doesn't really matter whether this part of the cylinder is close to the sheet or not. You could be an inch, another inch, even a mile. Because how big is a mile compared to infinity? You're still pretty close. And so the argument is something like this. If this wall is the infinitely charged sheet, if you stood here versus here, versus here, doesn't the charge distribution essentially look the same? And so my argument, as before, is that everywhere on surface number 1, the electric field is the same value. And the second part of the argument is anywhere on that surface number 1, the field should be pointing straight out. Why? Well, we're back to our symmetry again. What if it wasn't? What if I was standing somewhere on the sheet and the electric field wasn't straight out? Maybe it was up a little bit. Well, imagine yourself flipping it over again. Now you would have the same charge distribution, because when you flip over an infinite sheet, it still looks like an infinite sheet. But all of a sudden now you have an electric field that's pointing down. Doesn't make sense how the same charge distribution at one time could have made it up, and then looking at it again makes it down. So the only way that can work is if the electric field was straight out. Fair enough? And so when you flip it over, you get the same charge distribution and you get the same direction to the field. And so that was our symmetry argument that we did last time. And so the angle must be 0. And so this first integral reduces down to that. Now, likewise, for surface number 2. Surface number 2, we've got the same thing just on the other side. The electric field's going that way. The value of the electric field everywhere on surface number 2 would be the same, whether I'm close to the surface or not, because it's an infinite sheet. The angle would be 0. And so number 2 becomes E times dA. And surface number 3 becomes 0 for the same reason that if the field is always going to be straight out from the surface, then as you take a curved face here, the dA right here points that way. Up here, the dA points up, but in either case, since the electric field is pointing out, that's 90 degrees. That's 90 degrees. The electric field does not penetrate surface 3 in any way with this geometry. And so this is what we did Thursday. We said these two would be the same. They would come out then to be 2 times EA, where A is the surface area of this Gaussian cylinder. And the total electric field then becomes sigma over 2 epsilon naught. So again, a few moments ago, notice we did not get the 2. We did not get the 2 because we did not have an electric field extending the other way in our conductor. But here, we did get it. Yeah. Why is it A? Oh, so when I bring this to the other side of the equation, this becomes E equals charge over the 2A epsilon. And what's this? Yeah, that is charge density. Charge per area. Okay. Okay, so you already knew that, but I thought I would repeat it. Question it if that was a wise use of time, because I know we got a lot more to cover in this class here. But that's what we did on Thursday, and that's what we kind of did, like I said, a half hour ago. So we did it again. Now, here's really where the problem comes in. The problem is we do not just have one sheet, we have 2. And so maybe I'll color code them here. Let me grab a blue and a green here. But if I was going to draw the electric field from these positive charges, which maybe I'll label in blue now, what would the electric field from just that sheet alone look like? Well, according to this, what is this equation telling me? It is telling me the electric field is essentially a constant, right? It goes in both directions. And what's really kind of neat here is it tells me that it doesn't matter how far you are from the sheet. You could be 1 inch or 1 mile from the sheet. Don't you get the same amount of the field? And this is why I said this is a good design. This gives us a nice uniform field. Now, of course, in reality, it would taper off because you never would have an infinite sheet. But it doesn't matter if you're 1 inch or a couple inches from it. If this is a big sheet, you can say that the field is pretty much the same value all the way out. Fair enough? And in reality, it's a little less than that. So, but as a first order, first generation, and in your case, first class on electricity and magnetism, that is a good number to get started with. Okay? And so that's the equation for the electric field that we'll be using here. And so now, I can draw this and say, okay, on the left side of my positive sheet, I would get an electric field that way. And on the right side, I'd get a field this way. Now, ignoring this sheet for a moment, that electric field would be over here, right? And it would even have the same value as over here. But I'll draw it in the three areas. This one creates a field to the left, in the middle, and to the right of these sheets. Fair enough? Again, if the color code helps here, I'll go ahead now and switch to green. And so as I go over to green, I will put my negative charge in green and ask the same question. What does the electric field look like from that second negatively charged sheet? Well, wouldn't it just be the same logic with the same equation? Except they're negative now. So which way does the field point? Yeah, towards the sheet instead of outward away from the sheet. All right, so towards the sheet. All right, so here on the right-hand side, the electric field would look this way. Here on the left-hand side, the sheet, or the field would look this way. Right? And the value here would be the same as the value here. Which would be the same as the value here, which was the same as the green ones. And now I think you begin to see it here. I'll switch over to black again and ask you, okay, what is the total electric field over here? 0. Do you see it? The two individual sheets each make an electric field. You put that together for the total. They're equal and opposite. They cancel off. That is just one of the neat properties of this geometry. There is no electric field outside of the sheets. Now, I only did the left, but can you see it on the right also? What's the electric field over here on the right? Yeah, that one's 0. Also. How about in the middle? Yeah, so in the middle, they work together. And it's 2 times sigma over 2 epsilon, which is just sigma over epsilon. And so there's my equation for the electric field between these two sheets. Warning, doesn't that look like the same equation we got for the electric field near a surface of a metal conductor? Yes, but this is not near the surface of a metal conductor. This is between 2 infinite sheets. Don't mix them together, right? And so be careful when you see those equations. Sometimes they have a 2, sometimes they don't. In fact, here they have a 2 if you have just one sheet and it's an insulating sheet. Here, even if it's an insulator but you're between the sheets, you get this equation, which is the same as we got when we were near the surface, okay, of a metal conductor. And we got an electric field. So like I said, this design is really nice. Notice what it has given us. It has given us an area of a uniform electric field between the two sheets. That's why it's going to become a good, useful engineering and experimental tool. It's a nice way of getting a uniform field, at least approximately a uniform field. And it's pretty easy to get. You just take 2 sheets, take charge off one, put them on the other. And it doesn't have fields that affect other things nearby. So I can run my experiment and not worry about my cell phone. You know, it's like, okay, I can do it. Or in the case of more realistic, I can set this up in my processor and I can set this little field up inside one transistor. And I don't really have to worry about the field inside of this one transistor, how it affects the next transistor. And hopefully then I can build the 2 transistors really close and I can start to put thousands and thousands and tens of thousands and hundreds of thousands of little transistors on one processor and make a whole integrated chip and not worry about how one field affects the other. And then if it does a little bit, well then that's what the 2nd generation and 3rd generation are for, to see how much do they affect and how else could I build it and change the construction so that my fields are taken into consideration each way along the next step. Well, maybe I better do 1 or 2 more and then call it quits, and then we'll get into this next chapter. But yeah, question. Oh, good point. So now that I got a field here, which is really what this chapter is about, how I get the field. But eventually, really what we want to do is now start putting things in the field and seeing how there's a force and how they move. Exactly. I would make this next step and say, all right, if I go ahead and put a charge in here, Q, then that charge Q is going to have a force on it. That force would be the charge Q times the electric field. Right? Let me ask you two questions here before we go too far. Make sure you caught this. What direction, left or right, is the electric field? To the right, huh? What direction is the force on that charge? Depends if it's positive or negative. I can't answer that, right? So I'll say it again. This is why we like to deal with the electric field. It's more fundamental. Get away from the force. We can't answer what direction the force is until we know what charge we put there. And that's not the part we want to know. We want to know what the direction of the field. So the field has a well-defined direction, even without putting another charge there. And so that's why we always deal with the fields here and not the forces. Okay? Because we do have an issue of, well, which way does it go? All right, so now I can ask a better question. If I were to put a positive charge between there, which way would the force go? To the right. If I put a negative charge in there, which way would it go? To the left. And you see then again that a negative charge times a field to the right gives me a vector to the left, right? And so you got to keep in mind here, and you're going to see this as we get started in the next chapter, that the negative charge moves opposite to the field. The positive charge is moved with the field. And that doesn't surprise you that positives and negatives move opposite in direction. But a lot of times when you draw pictures, when you draw the pictures, you just naturally see the arrow that way. And you go, oh, it's going to move that way. And you think of it as a force. And it's an easy mistake to fall. In fact, a few years ago, I saw what looked like a cool t-shirt. I guess it was still a cool t-shirt. But one of the students was wearing it. And I go, where did you get that shirt? It had all kinds of equations and symbols, and it had this electric field, you know. And it was a picture of an electron gun. We'll be talking about shooting in electrons, negative charges, right? And he goes, oh, yeah, our high school physics class had it made up. Oh, that's cool. Except they showed the motion of the electron in the same direction as the field. On their shirts. So it was a little. Unfortunately, they did cut it. He was telling me, he goes, yeah, actually, we did notice that. So it's like only some of the shirts are this way. The other ones were fixed before we had them all printed there. So it must have been like the first year, the first generation of it. So, but it's easy to do. And again, you're going to see that more so in the next chapter. We really want to focus so much on the field, not the force. Eventually we do, and that was really your question. Eventually we are going to put a charge here, and eventually we do want to figure out what the force is on it. But we haven't really been talking about what the force is on it. We've been talking about what the field is created by the other charges, for just that reason. All right, well, let me try. Here's a fun one to do. Here's going to involve a little more calculus. And so again, I'll kind of shift gears here again. Let's see if we can do this one. And this is a magenta one, and it has a variable charge density, and so this will be a good place to stop. Or maybe I'll do a second one like that and call it a good place to stop here. We don't really have a picture in the book, so I won't change the diagram here, but here's what the problem says in number 58. It says, an infinitely long insulating cylinder of radius r. Now let me stop right there. It's insulating. What does that mean different than a conductor? Okay, the charges don't move, but it also means, what about the inside of this cylinder? Yeah, there could be an electric field. I don't know if there is because I haven't read the rest of the problem, but there could be an electric field inside, and there could be charges spread out with inside the cylinder. That could not happen with a conductor. So keep that in mind. If they would have said this is a conductor, they would have just told me the charge distribution, right? It's on the surface. Now, they didn't say that. All right. An infinitely long insulating cylinder of radius r has a volumetric charge density that changes with radius given by this equation. Well, let me pause there. All right. So I'm going to draw cylinder that you might say is infinitely long. I'll put the axis of symmetry here. But what they're saying is that there is a charge density. It changes, okay? It's not all on the surface because it's not a conductor. But it changes. It changes how? Well, it changes according to this equation. There's some constant, rho naught, and they write it as A minus R over B. And what they mean by this, and I guess I should keep reading, they say a charge density that varies according to this equation, where rho naught, A and B, are positive constants, and R is the distance from the axis of symmetry of the cylinder. Use Gauss' law, determine the magnitude of the electric field, both inside and outside the cylinder. Okay? Now, before we even try Gauss's law, do you see what they're saying about the charge density? You see how it varies, right? Well, what they're really saying here is if I were to make a graph and I were to plot the charge density as a function of R, right at the center, when R is 0, what is the charge density? Right here. What does this equation say? If R is 0, what do you get? Well, you get rho naught times A, right? All right, so what they're saying here is near this center, there's a certain charge density. And what will happen as I go out? Will the charge density change? Will it increase or decrease? Decrease. And in what kind of shape? What kind of pattern would this look like? Well, isn't that the equation of a line, right? If it tapers down? Let's see. Do they give radius a uniform charge density of radius capital R? So what I'm going to do is I'm going to be moving out, and it's going to have something that looks like that, right? Gets less and less and less. And they don't say it goes all the way down to 0. I thought they were going to say that. But they don't. They just say, look, it's as you move out, it's getting less and less and less. So maybe I'll just go this far. And so at this point, I will be at capital, radius capital R. Fair enough? And then so if I come across here, I guess this would be rho naught A minus R over B would be the final charge density when I get to the other side, when I get to capital R. I'm still bothered. So they don't give me any more kind of hints about A and B, huh? I was hoping they'd tie them together with R, but I don't see it. All right, so that's all they're going to say here. Okay. All right, so a lot of charge, tapers off as I go. Probably a more realistic problem than what we usually get, and we just say, oh, it's uniformly charged distribution. Because as you're manufacturing this, you can actually, usually you lay down the material and you put a lot of charge in there, and as you lay down the material, with temperature and with time, it migrates out. And so there tends to be a high concentration, and because of diffusion, it kind of tapers off. Not necessarily in a linear fashion, but that's the easiest mathematical to deal one that's not constant. And so it kind of changes as we get further out here. And so they've given me this charge distribution. But in our case, we are asked to use Gauss's law. So again, let's find the electric field from something like this. What is the electric field? So the electric field would be solved from here. And I'll say it again. Do you want the answers to all the homework problems for this chapter, right? There it is. And it looks like a lot of you already got it. And it sounds like some of you are still working on it here. But we just need to do that and apply it to this situation. So let's apply it to, and I don't know, you want to do inside or outside first? Anybody care? All right, I heard some people saying inside. All right, so let's do inside. So let me grab a pen here. and draw a Gaussian surface. And so here's my Gaussian surface. My Gaussian surface extends out to some radius r. It has a length of L. And then that should give me a way of finding the electric field on that Gaussian surface. And then by extension of that, I could probably see that it would give me the same equation no matter where I drew that Gaussian surface, as long as it was inside. So it'll probably give me the equation for everywhere inside. Even though I'm going to solve it for just one surface at the beginning, when I'm all done, I will look at that and say, well, that would be the same step I would take at any radius. And so r is my variable, and so it changes with r. But again, the reason I picked that Gaussian surface is because what do you know about the electric field? What can you do in terms of symmetry? Well, if you look closely at the charge distribution, what they're saying is it's very concentrated in the center and tapers off as you go out. But it doesn't matter in what direction you go out, it tapers off the same, right? So, again, if this pole represents the center of the cylinder, and I am inside the cylinder, so the edge of the charge distribution is behind me, if I look at this, I will see charge increasing and reaching its maximum at the center, decreasing on behind me, and the same thing radially outward from every point there. If I move somewhere else, but am still in the cylinder and still the same distance away, don't I see the same charge distribution? Don't I see a very high charge here, getting less as it comes to me, tapering even lower as it goes behind me, and the same thing radially outward? So again, my argument would be from symmetry that as I stand here, whatever electric field I get here, I would also get here. And anywhere else on the surface, what I've been calling the face of the cylinder, the part that wraps around. And so, when I take this integral and I break it down into a top piece and a bottom piece and the rounded part, the face piece, I am going to argue that this rounded part, the electric field on that surface is a constant, and I can pull it out. That was my first argument here. And when I get into the direction of the electric field, I could again use the principles of symmetry here and say, look, when I get here, if this is a set of positive charges, all of those in front of me would make the field out that way. Yes, there's charges behind me. They're going to be going that way, but I would predict that there's more in front of me. It kind of really, kind of depends on where this breaks apart. But certainly when I got in the middle here, there would be an equal amount on that side and this side. And so I'd expect the electric field to be zero here in the middle, yes. But as I got out to, say, here or to here, I expect the electric field out that way, right? And I never expect the electric field to kind of be up a little bit or sideways a little bit. Because if it was, say, sideways, and I take that cylinder and I flip it over, I get the same charge distribution, but all of a sudden now I have an electric field going in the other direction. And that couldn't happen. I couldn't have the same charge distribution and end up with a different electric field. So that tells me the electric field has to be radially outward. And so as I flip this over, I still have a radially outward. So I know the electric field is going to be radially outward. So when I take this dot product, everywhere on this rounded surface, it's going to be 0 degrees. And in fact, that helps me with top and bottom. What would that tell me about the angle on the top? 90 degrees. Bottom, also 90 degrees, right? Now, I would not argue that everywhere on the top the electric field is a constant, because the top, as I walk along the top, I'm getting closer to the center. And I would think the electric field would get a little smaller as I got closer to the center, because I'm getting kind of a balance between charges on one side and the other. And as I got out to here, I got so much charges on one side of me. And so I would not expect the electric field to be a constant along the top, but I would expect it to be that way, and dA is up. And so the angle is 0. So as far as flux goes, I still get a 0 there and a 0 there. Okay. And so this side of the equation becomes the electric field on this Gaussian surface times the area. Well, the area of that Gaussian surface is the area of the face from a cylinder, which is its circumference, 2 pi r, times its length L. Also, as we did before on a problem like this, when I'm all done with this problem, I hope that L doesn't show up. Why not? Yeah, the L is part of my mathematics, right? It's part of my Gaussian surface. The electric field should have been determined by the charge distribution. So I expect an equation that has things in it like rho naught and A and B and then distance R. But I don't expect an L to be in there. I expect to really get the same results regardless of what L is. So we'll see if that's true when it all goes away here. Okay? But here's the harder part of the problem. Here's why I picked this. The right-hand side of the equation says it's got to be the charge inside the Gaussian surface. How do I get the charge inside the Gaussian surface? Yeah. And so you may think of the total charge inside as the sum of a bunch of little charges. And so I need to add up all of these little charges, right? Now, you can think of that then as density times volume, since our definition of density is charge per volume. And so we'll do a substitution here. I think it's easiest to start here. Total charge is the sum of all the charges inside. That changes to density times the volume that is inside. And now I can actually put the equation that they gave me. They gave me an equation for the density. It is rho naught A minus R over B, and then dV. And so that's what's different, I think, than any problem I've done in class so far, is we've got a varying charge density. And I can't pull it out in front of the equation. But nonetheless, I know it. And so it's really kind of the same problem now. I just got to put it in and do my integral here. Okay. I won't bother to pull out my constants quite yet, because now I should ask myself this. What is the volumes that I'm adding up? Yeah, and they gave me a helpful clue here. Their charge density changes with the radius. So if I were to take on the inside of this Gaussian surface another cylinder-looking shell, wouldn't the charge density on that shell be the same all the way across that surface? So if you made this shell a thickness of dr, couldn't you then say that the little bit of volume that I am going to be adding together is really the volume of a shell, and then I'm just going to add a small radius shell, a bigger, and a bigger, and a bigger, and bigger, until I get to the edge of the Gaussian surface, and then that's going to give me all my charge in a Gaussian surface? And so there's our calculus, a shell plus a shell plus a shell plus a shell. And so, take somebody's homework here, right? Visual, this is my first shell, right? And what's the volume of that? And then I will make it a little bigger. That one, and a little bigger. And that one, and a shell plus a shell plus a shell plus a shell, until I get that whole volume, not of the whole cylinder where the charge is, but of the Gaussian surface, because I want to know how much charge is inside of the Gaussian surface. So I'm only going to go to the edge of the Gaussian surface. Okay? So that is my key right here. This then is, how do I get a volume of a shell? Well, I guess it's the circumference, 2 pi r, times its length, L, times its thickness, dr. And so this is what I've kind of been showing you for the last 2 weeks. This is how we get the volume, right? We look at the geometry. Length times width times thickness, okay? And so there is my volume. And what's nice is I now have a dr, finally, right? I started with what is a dq, which I think makes a lot of sense conceptually. Just add up the dq's to get the total q. I like that. That's a good place to start. But mathematically, it's not very helpful. So you have to change that dq into a dr. And that's how I did it. The dq became a dv. The dv then became a dr. And what would be my limits of my integral? Now, would I go all the way to big R or little r? Yeah, I'd say little r in this case. Why? Yeah, so here I'm not trying to go all the way outside here. I'm trying to find what is the charge inside the Gaussian surface. So I'm only going to go to little r. I've kind of run out of room here for this problem, but oh, maybe just as well. I don't need this anymore. All right. But now I can do this integral and eventually put it back over there where I'm trying to solve for. But here is my integral. Let me start by pulling the 2 pi and the rho naught out in front. So the 2 pi I'll pull out in front, the rho, oh, even the L. And I'll do the L. So the first term is really an A times an R. Well, that becomes R squared over 2 evaluated from 0 to R. And then the second one becomes an R squared. So when I integrate it, it becomes an R cubed over 3. And then, of course, it has the B with it. Evaluated from 0 to R if you like that. But now I've got my 2 pi rho naught. I've got my L. And it looks like I've got an AR squared over 2 minus R cubed over 3B. It doesn't look like I can do much simplifying from that, or at least until I put it back into here. So when I come over to here, now that I have solved for what charge is inside of my Gaussian surface, I can then do 2 pi rho naught L times AR squared over 2 minus R cubed over 3B. And again, they didn't give me any kind of connection between B and A, so I don't think there's much I can do other than now, as I simplify it, notice there's an L on each side. Yay, right? That's what I was saying. We really want the L's to go away. The L's should have never shown up in the final answer. We kind of expect that. The L's was just our mathematical creation here to get this to work out. The 2 pi's are going to cancel off. And the R over here will cancel with 1 on each of those. And so my answer for what is the electric field on the inside anyways is 1 over epsilon naught. And it looks like I have an AR over 2 minus an A squared over 3B. Right? Yeah. Pardon me? Oh, yeah, what happened to rho naught? Oh, should be right there. Right there. Yeah. Okay. And so that would be the electric field. And if it kind of fits our intuition, which I think it does here, this would say the electric field is what as a function of R. And it's only valid because we're on the inside until we get to capital R. But it looks like it is telling me something very useful. What happens right at the center when R is 0? The electric field is 0. And that's kind of what I expected, right? Right in the center here, I expect the charges left and right. They're going to cancel off. As I move away, I've got this one increasing and this one decreasing, although this is linear and this is quadratic, so it looks like a parabola. But a parabola that would look like and who knows when it starts to tilt over, because I don't know the numbers there, but at some point it would go like that, but my equation's, not valid there. But it's kind of what I expected. I expected increase, increase, increase. And at some point maybe even decreasing, because I'm getting far away from the charges in the middle, where a lot of the charges kind of depends on the values of A and B. And then, of course, the second half of this problem is, all right, what is the equation for the electric field on the outside? So everything I've done here is for R less than capital R, right? The electric field inside. So let's try it again and ask what would change. What if we go to the outside? And so, new Gaussian surface. Here's my Gaussian surface. Again, I'll say the Gaussian surface has a radius of little r. Would this change on the outside? No, that's Gauss's surface. How about this line? Would this line change? Now, I'm still going to make a cylinder. It's still going to have a top, a bottom, and a face. I haven't done anything with that side of the equation yet. So as I look at this, I would still argue that the face wraps around, giving me an electric field that is a constant everywhere along the face, and it points radially outward. So those two are the same. I would also argue that top and bottom, there is still 90 degrees. So nothing changes with my Gaussian surface as I go to the outside. And so I would still get this line, which would be E 2 pi little r times L. Fair enough? But what about here? Would this change? Mm-hmm. The charge inside would be different, right? Now, I still would have the same charge density, but let's come over here on the outside. Would this line still be good? Right? The charge on the inside is nothing but a sum of a bunch of charges, which is the density times the volume. I can put in the equation for the density times the volume, so that's still good. Anything change here? Yeah, here's where a change starts. What changes here? You see it? So do I put a big R here, big R here, big R here? Yeah, and really the only thing that changes is that there's a big R in the limit. I'm still going to add shells that have this volume with this density. And I'm going to be adding them up and adding them up and adding them up and adding them up. And the only difference is I am not going to add them up all the way to the edge of the Gaussian surface. I'm not going to add them up to little r. When do I stop? At big R, right? I stop where the cylinder stops. Okay, and that's the difference. So that means in this line, I've got 0 to capital R. I've got 0 to capital R. Which means in this line, I've got capital R squared. And this line, I have capital R cubed. And that's really the only difference in this problem.
Not necessarily, right? Because back in the integration, we still have the little r from the other side.
Okay, so now, if it'll be okay, I can't cancel the r's on the opposite side. And that's what I really wanted you to see here. You've got to be careful about your r's, whether we're dealing with the little r or the big R. So back in this line right here, where I had little r's, and the little r cancels with that little r, all that's going to be different. And that's where the big change occurred, right there. The big change is right there. To get the charge inside, I only add up to the edge of the cylinder. And so this equation does not have little r's in it. It only has capital R's in it. So back here, let me just kind of clean it up a little bit. This is the 2 pi little r L. This side is still the 2 pi rho naught L from the first part. But right here, this is a capital R squared, and this is a capital R cubed. And so now, the 2 pi and the L cancels off, and good, the L still cancels off for the same reason. I don't want to see an L when I'm all done here. But there is no little r here, and that's a little r, and I don't want to mix the little r with the big R, so my final step for the electric field on the outside is something more along this line, rho naught over epsilon naught times little r times this, which is just a constant number, by the way, does not change. It's got the r's and the b and the a. And so once I get on the outside for r, little r greater than big R, I begin to see a different equation for the electric field. How does the electric field change? Well, it is inversely proportional to R. And so if the electric field had tapered off, say, to there, this dotted line would not continue. That was the equation we had for the inside. But now that we're on the outside, we've got a whole new equation. And on the outside, it would look like this. Right? And it would have a 1 over R value. And that hopefully is not a surprise. That's the same function of the electric field we saw when we had a uniform charge distribution. And so on the outside, we would kind of expect it to be tapering off, just like we saw for the spheres, we saw it tapering off. Well, bummer. Because I did want to start the chapter. But I don't think if I start it now, you guys will remember anything I say on Thursday. You got a brain full, and it needs to be shoved down for the next couple of days. So we'll stop there, 10 minutes early. Don't let the rumor get out, because people will start thinking this is an easy class. And we really don't have room for people to come signing up here. So don't let anybody know we let you out early.